Hey guys, what's up? Welcome to another video of CHE 101, and today we will be talking about reactor design for multiple reactions, specifically for series reactions. Okay. So we will be using the same set of equations and formulas, just like the ones used in reactor design for single reactions. So let's now proceed to the problem. So given the elementary reaction A forming B forming C, which is a series reaction with K1 equal to 0.3 per R and K2 equal to 0.1 per R, the feed stream contains only 2 moles per liter of A charged at a rate of 4 moles per R. So what are the final concentrations of A, B, and C if two 3.5 liter CSTRs in series is used? So we write first the given. We have the following rate constants, and then we have the initial concentration of A, which is 2 moles per liter, and then the feed rate, which is at 4 moles per hour. And then we have the volume of the two CSTRs, which both have a volume of 3.5 liters. So we need to find the final concentrations of A, B, and C. So to illustrate this, the problem looks like this. So we're charging here 2 moles per liter of A, and then we don't have B and C. And then let's say the exit concentrations at the first reactor are CA1, CB1, and CC1. And then at the final, this is CA2, or let's use CAF, CBF, and CCF. Okay, then each reactor has a volume of 3.5 liters. Okay, so first, let's write the rate law for each species in the reaction. So for A, since we have a unit of per hour for the K1, then that means the reaction is first order. Okay, so for the rate of disappearance of A, this is simply K1 Ca or 0.3 Ca. For B, the formation of B is equal to K1 Ca minus K2 Cb. So that's 0.3 Ca minus 0.1 Cb. Finally, for C, that's simply K2 Cb or 0.1 Cb. Right. So now we use the feed rate, the molar feed rate, and the concentration to get the volumetric flow rate. So that's simply V sub O equal to FAO all over CAO. So this is 4 moles per hour all over 2 moles per liter. And this should give you 2 liters per hour. And then finally, we get the space-time. So that's tau equals V over VO. So for each reactor, the space-time is equal to tau, which is 3.5 all over 3.5 liters all over 2 liters per hour. So that's 1.75 hours. Now, the space-time can be represented in terms of A from the formulas shown earlier. CAO minus CA all over negative RA. In terms of B, this is equal to CB minus CBO all over R sub B. And finally, for C, it's the same as B. Okay, so now we get the concentrations at the first exit of the first reactor first. So for the first reactor, okay, we write CA1. So for CA1, tau equals CAO minus CA1 all over negative RA at CA1. So that will be 2 minus CA1 all over 0.3 times CA1. And this should equal 1.75. So CA1 here should be 1.3115. For CB1, that should be CB1 minus CB0 is 0, and then RB is 0.3 CA, so 0.3 times 1.3115 minus 0.1 CB1 equal to 1.75. And this should give you CB1 equal to 0.5860. Finally, for CC1, so that's CC1 minus 0 all over 0.1 CB1. So that's 0.1 times 0.5860 equal to 1.75. So CC1 is equal to 0.1025. So if you add these three, you should get a total concentration of 2. So I leave the checking part to you guys. Now, at the exit of the second reactor, so this is now where we compute the CAF, CBF, and CCF. So CAF, so this time the concentration of A entering the second reactor is now CA1. So instead of writing CAO minus CA1, we write now CA1 minus CA2. So that will be, okay, so let me write that down. Negative RA at this is CA2. Okay, so 1.3115 minus CA2 all over 0.3 times CA2 is equal to 1.75. And this should give you CAF. So here CAF and CA2 are just the same. All right. So CAF is equal to 0.86 moles per liter. Now CBF, this time it's CB2 minus CB1 all over R sub B at CB2. So this is equal to CB2 minus 0.5860 all over 0.3 CA2. So that's 0.3 times 0.86 minus 0.1 CB2 equal to 1.75. And this should give you CBF equal to 0.8830. Finally, for CCF, that's CC2 minus CC1 all over RC at CC2. So this is simply CC2 minus 0.1025 all over 0.1 CB2. So that's 0.1 of 0.8830 equal to 1.75 again. And this should give you CCF equal to 0.2570 moles per liter. Again, the exit concentrations should have a sum of 2 moles per liter. And that's it for this problem. So in this video, we discussed how to deal with series reactions in a series of CSTRs. So thank you guys for watching, and I hope you learned something from this video.